In this video, we want to derive the geodesic equation in a different way with respect to the usual way, which considers an action, and then starting from an action, the geodesic equation is derived. But in this case, we are going to start from an inertial reference frame. In an inertial reference frame, we have that if there are no forces acting on some particle, the acceleration of the particle x double dot of I is equal to 0. In this case, I can be either 1, 2, and 3. One of these indices because it can be a position, right? And if we also consider time, which is the fourth component, we can also write x double dot mu equal to 0 because x4, if we define it as t, for example, when the speed of light is equal to 1, in an inertial frame, we have that the second derivative of time with respect to time is equal to 0. So we can put this equation together with this one, and this will give us x double dot mu equal to 0. Now, if we want to go to a general frame, we can start from here, and we can try to rewrite it by changing frame of reference. First, we start in this fashion. So we have the second derivative of x mu with respect to, in this case, instead of time t, we are going to consider proper time tau, because we want to find something that is invariant. We want to find an equation that we can write in the same form in every reference frame. So it makes sense that we can replace t, which is something true only in a certain reference frame, with tau. Now we can rewrite this equation like this, derivative with respect to tau of, then here we have dx mu d tau, but we can rewrite that in another frame of reference like this, dx mu dy nu, and then here we have dy nu d tau. I have simply changed frame of reference. We go from x mu to y nu, a new frame of reference. And now, for the sake of convenience, let me rewrite dy nu d tau as y dot nu. So this dot here represents derivatives with respect to proper time. So this is just convenience. And this is equal to 0, but we can rewrite this by taking another derivative. If we take this derivative, we can rewrite the equation like this: d squared x mu with respect to y sigma with respect to y nu, y dot sigma, y dot nu, plus, then we have dx mu dy nu y double dot nu equal to 0. Now I'm going to take the inverse of this matrix. So in particular, I'm going to multiply both sides, actually both terms, this term here and this term here, by dy alpha over dx mu. So if I multiply by this term, I'm going to get rid of this, because this term multiplied by this is going to give me a Kronecker delta alpha nu. So when I consider this multiplication, I get dy alpha over dx mu, I get d squared x mu, dy sigma, dy nu, y dot sigma, y dot nu, and then here I have plus the Kronecker delta alpha nu times y double dot nu equal to 0. But I can rewrite this term like this: y double dot alpha. Simple as that. Now, let's rewrite this expression in another way. let's start from this. We know that dy alpha g alpha beta dy beta, in this case, we are in a frame where the matrix G, or simply the metric tensor G alpha beta, might be different from the Lorentz metric, because y alpha can be a very general coordinate system. But since this is ds squared, the invariant ds squared, that is equal to c squared d tau squared, and when the speed of light is equal to 1, this is of course equal to d tau squared. So when we think of d tau squared, it's the same as ds squared. It's not really important. So this is the case where c is equal to 1, and this is also equal to dx mu era mu nu, which is the Lorentz metric, dx nu, because x mu is an inertial frame. So in an inertial frame, we have the Lorentz metric written like this. And from here, if we take the partial derivative of y alpha with respect to x mu, g alpha beta, dy beta, this is equal to era mu nu dx nu. And we can rewrite this like this. We have g alpha beta dy alpha dx mu is equal to era mu nu dx nu over dy beta, and this can be rewritten like this. If we take the inverse of this metric tensor, we get dy alpha dx mu equal to g alpha beta era mu tau dx tau dy beta. So I have changed this index nu here only for the sake of convenience, because when I replace this expression there, I don't want to get multiple indices. So for example, here I already have nu and nu, so I want to change the name of some indices just for the sake of convenience, in order to not mess up all my indices. I cannot repeat this index nu multiple times, so I can just have two of those indices, here and here, just one time. But let's do the calculation. So I'm going to replace dy alpha dx mu here with this expression. So I have g alpha beta era mu tau dx tau dy beta times d squared x mu with respect to dy sigma dy nu y dot sigma y dot nu plus y double dot alpha equal to 0. And now you can check that we can rewrite this first term in another fashion. So I'm going to rewrite the first term like this. We have g alpha beta, which remains the same. Then we divide by 2, and then we get square bracket derivative with respect to y sigma dx tau dy beta era mu tau. Remember that this is a constant metric tensor, so it's made up of diagonal terms which can be either +1 or -1. And then here we have dx mu dy nu plus d over dy nu dx tau dy beta era mu tau dx mu dy sigma plus, and then I'm going to rewrite the expression here, minus derivative with respect to y beta, derivative of x tau with respect to y sigma, eta mu tau, derivative of x mu with respect to y nu, times this same part, y dot sigma y dot nu plus y double dot alpha equal to 0. So you can check. It's very easy to do this, actually. This is just a matter of a simple calculation. You can check that if you multiply this expression, if you consider the derivatives, and then you just write out this part, you can check that it is equal to this first part here. It is no issue to demonstrate that. It is quite easy to do that. And it is not really important to do it here. I'm not going to do all the calculations, but if you know how to deal with tensors, this is quite trivial. And now you can check that inside this expression here, this is none other than g beta nu. Whereas here we have g beta sigma, or g sigma beta. It's the same because they are symmetric. These terms are symmetric, the g beta nu and g beta sigma. And here we have g sigma nu. So finally, we have this expression. We have 1/2 g alpha beta, derivative of g beta nu with respect to y sigma, plus derivative of g beta sigma with respect to y nu, minus derivative of g nu sigma with respect to y beta, y dot sigma y dot nu plus y double dot alpha equal to 0. Now, what's this one? This term here. What is this? This is none other than the Christoffel symbol. It's the Christoffel symbol that we usually call with the letter gamma. We denote it with the letter gamma. So it's gamma, alpha, sigma nu, or nu sigma. It's the same if you exchange the order between these two indices because it's symmetric with respect to these two indices. And according to Einstein, for example, he used minus this term. So it's just a definition. But to be consistent with the most of books that you see in the literature, it's usually defined like this, with a plus sign, and then we get gamma, alpha, sigma, nu. So the equation is y double dot alpha plus gamma, alpha, sigma, nu, y dot sigma, y dot nu equal to 0. And this is none other than the geodetic equation written in a general form, where you see the appearance of the Christoffel symbol.